Hi, this is Seb, and this is a pipe magma petroleum boiler. A petroleum boiler turns crude oil into petroleum. So we can see, let's see, where's the crude oil? We can see the crude oil, which are the black dots coming up this pipe here, turn into petroleum, which counterflows in yellow here, all the way back down, gets picked up by this pump, and pumped out here, presumably to go to your petroleum generators. And this is a piped magma petroleum boiler because it uses magma that is in pipes coming here. So we have a liquid reservoir here that's full of magma, and you can see right now the magma is flowing and heating up the what I call the kettle or the pot here to 403 degrees or so, and that's the temperature at which crude oil turns into petroleum. Most other boilers do not use magma in pipes. Instead, one uses magma as a liquid in the environment, like so, and then you dump the magma somewhere here. But because you have to move the magma around and it's not in pipes, you have to use the mechanized airlocks like this, and you can move the magma around with these mechanized airlocks. But when the magma freezes or turns into igneous rock at 1400 degrees, it will no longer move because it's not a liquid anymore. And then you need to have a robo miner like this to dig out the magma once it gets too cold. Um, so when you have the magma in a pipe, you do not need to dig it out. You do not need to move it around with mechanized airlocks. You just use the magma to heat up your crude oil, and you dispose of the cooled igneous rock. We can see it down here as it's a igneous rock debris that's been used up, and it's at 244 degrees. In a previous video, I've discussed in detail how you can put magma into pipes. I'll put the link in the description. I've described in detail how you can put magma into a pipe, and I'll briefly mention it in this video, but please look at the other video for details. And the advantage is that once you have it in a pipe, you don't have to worry about phase changes, provided that the flow of the magma in the pipe is less than 1 kilogram per second, which is why I have these liquid valves here. So this one is 3 kilograms per second, and each one of these is at 1 kilograms per second. And if there's 1 kilogram per second of magma in a pipe, then it's not going to freeze. So if we see here, these pipes are carrying 1 kilogram per second, and the magma is at 400 degrees, which is much below the freezing point of magma. And here it's at 200 degrees. The same magma is at 200 degrees or so. And it doesn't crack the pipes. And that's because there's the mechanic and oxygen not included, that if you transport 1 kilogram per second or less in a pipe, then the liquid will not change phase. It won't vaporize and it won't solidify in the pipe. And this allows us to make a maximal use of our magma, because if you use magma in the environment this way, often once the magma drops below, or the igneous rock drops below about 600 degrees, it can no longer be used to boil crude oil. But because we've got it in pipes and it doesn't really do any phase changes, we're actually able to use up the magma all the way down to 240 degrees, which gives us a little bit more energy and a little bit more efficiency. And another advantage is because the because of this, because we don't have to deal with all these robo miners and mechanized airlocks to move the magma around. I think that the overall machine, the overall boiler is slightly simpler than it would otherwise be. But perhaps the disadvantage is that we are limited in the amount of magma that we can bring in here to warm up the machine, which is important when you start it, because when you start it, there's a large amount of mass that is present here that is going to be very cold, and you need to bring it up to operating temperature, which is just about 400 degrees. If you were to fill, for example, these tiles here are full of steam. There's 1 ton of steam per tile. If you were to fill these tiles with magma instead, then this would instantly become quite possibly too hot. Um, but you can bring the temperature up much more quickly by dumping an enormous amount of magma into the machine, whereas here we're limited to 3 kilograms per second with these 3 pipes. Now this is not the simplest machine that you can make, because you could have just 1 pipe here, because this machine requires roughly 540 grams per second of magma. So it can definitely fit into one of these 1 kilogram per second pipes. But when you start this machine up, as I said, you need to bring everything up to temperature. Okay, now I'm going to show you how you start this thing. So first I'm going to assume that you have a liquid reservoir that's got some magma in it, and a pipe and everything that you need to replenish this. So I'm not going to explain how to start the pump. My pipes here are already full of crude oil, and so this thermosensor here is at 401 and above, which right now means that no magma is flowing, and this hydrosensor is at 850 and above, so that there's no crude oil coming for now. So the first step is to fill so that there's about 500 kilogram per tile of crude oil. So let's do this. Okay, now I have 500 kilograms, 520 kilograms. So now I'm ready to start bringing the magma in. So now we're going to turn this to below. Right now it's at 41 degrees, so we're going to click on the below, and that will start the magma flowing, and it was going to flow until it hits 401 degrees, which is basically when this contraption is ready to go. So, and this will take maybe a couple of cycles. Okay, so now we have our first little bit of steam that's formed in this water reservoir. Now, in case I didn't say already, the reason why there's water here is because this is a really cheap way of putting a lot of mass in our system. Water, 1 tile of water is 1,000 kilogram. And if we compare, for example, a window tile here is 100 kilograms. So the water is 10 times more massive, which means that we get a lot of mass here. And this is really great when you build any sort of contraption, and oxygen not included. If you want to have more regular temperatures that don't vary so much, you just put a lot of mass. And so water is really cheap. It's easy to put there. You just turn it into steam. Okay, so now all the water's turned into steam. It's 127 degrees now, so we're just waiting for it to reach the operating temperature of 400. Well, the steam itself is going to be quite a bit more than 401 degrees. It'll be maybe 415 degrees, I believe. So let's wait. Alright, so it's been just about 2 cycles now, and the crude oil is just starting to flash into petroleum. Not quite completely. And so now there it is. So now it's all petroleum, and so now we can bring in more crude oil by switching back this to below. And at this point now, it's fully automatic. So now we just wait. This tile is going to fill with crude oil that's going to be a little bit too cold, with 850 kilograms of crude oil, and then the liquid vent is going to shut, and then it's going to heat up again and turn into petroleum, and it's going to repeat this process until the cook pot here, the little kettle that boils the crude oil into petroleum, is completely full and overflows and spills down all the way down to the pump. So let's wait for that to happen. It might take another, maybe the rest of this cycle, I'm not sure. So now we get the petroleum spilling down the heat exchange, and at this point we should no longer get any interruptions in the crude oil, or maybe a little bit, but almost none at all. And we're just about to start pumping out the petroleum, which would be sent to our petroleum generators. And this procedure has taken not quite 3 cycles. So, but if so, we have 3 pipes of magma coming in, which means that we have about 3 kilograms per second of magma to heat up so that we reach our operating temperature, which we have now reached. But if one had only one pipe, one might expect for it to take 3 times as long. So instead of almost 3 cycles, it would be almost 9 cycles for it to start up. When the system initially starts up, we can see that the petroleum pipe that's coming out is not at full capacity. We're not getting a 10 kilograms per second. At least not every bead of it is 10 kilograms. This is because, yes, the crude oil coming in is 10 kilograms per second, but this petroleum that's flowing in the environment takes a little bit of time for the mass to stabilize and to reach equilibrium. So just a guess here that in about 1 or 2 more cycles, we're going to get very, very even 10 kilograms per second. Although already here with this flow, you can get quite a bit of power generation from your petroleum generators here. Maybe not 5 petroleum generators, but 2 or 3 seems like reasonable. It's now been, I believe, 3.5 cycles since I've turned this on, and we seem to have reached operating mass so that we have 10 kilograms per second of petroleum in every bead of petroleum coming out of the petroleum pump. This bit at the bottom here is my garbage dump, and you can see that the igneous rock comes out here as little chunks of debris. And you could open the side here so that your dupes could come in and pick this up and carry it with the rest of your igneous rock, or use it to build your base, and that would be fine. I mean, it's a bit hot, but other than that, it's fine. But you might be wondering why this sort of garbage dump looks a little bit funny. Let me put back these tiles that I removed. Why did I put here non-insulated tiles of igneous rock, and why did I put some temp shift plates? There's I don't know if it's a feature or a glitch or a bug, but even though you're allowed to transport supercooled fluids in your pipes, like this magma here at 200 degrees, if you have quite a cold magma that falls out of a vent here and lands on an insulated tile, and because the tile is insulated, it's not really going to exchange heat with the magma, or a very, very small amount of heat is going to be exchanged, especially if the magma is cold enough. And for some weird reason, the game only causes the phase change to happen when the temperature of the fluid changes. So the magma would come out, let's say, at 40 degrees and land on an insulated tile and stay forever at 40 degrees, and the game would never check to see if the fluid is too cold and should, become a solid. And so you can end up with like these pools of liquid magma at 20 degrees. But as soon as you cause the magma to interact with a material and change its temperature, then immediately it will check the temperature and cause it to become igneous rock because it's too cold. And so that's why I created a garbage dump like this, is because it was bothering me to see all this liquid 40 degree magma or 200 degree magma. I was just kind of bothered, but you don't really need to do that if you don't like it. On the other hand, there is a bigger possible problem, and it's not specific to this particular boiler, but every boiler that I've seen produces these kind of igneous rock debris that come out of this apparatus. And again, I don't know if it's a glitch in the game or if it could be a feature, but I've noticed. So you may have done the same thing as I do, which is when you have when you start to get into the mid game or the late game, and there's so much debris on the map that the game starts having trouble, everything slows down and it's very hard to play, what you do is you put sweep orders and you collect all the debris into one place, perhaps even just one tile or just a few tiles, and then your game runs faster. But it's seemingly randomly when there's large pieces of debris. So here I've got my mouse over a 5-ton piece of igneous rock, and this will keep on increasing, and then by and by there will be multiple pieces of igneous rock here that will weigh many tons. Sometimes the game turns these very large masses of debris back into natural tiles, and you can I see this in my survival games with my base, when I've swept everything into just a few tiles where I have got like all my debris in just a few locations, and they seemingly randomly solidify into natural tiles, which is sometimes it's a shame, because if you're trying to save this material to build your base, when they're a natural tile, you need to dig them out, and when you dig them out, you lose half of the mass. Now, this is igneous rock here, so it's not too precious, so it's not such a big concern. But in principle, if none of your dupes come in here to clean this up, in principle, these could glitch into natural tiles and eventually could fill the garbage dump. And this is not specific to this build. It occurs in any build of a petroleum boiler where uh, igneous rock debris is ejected somewhere in this way. And as far as I know, all of the magma-based petroleum boilers do dispose of igneous rock debris somehow. So this is a copy of the system that I've instrumented to try to measure the efficiency of um, of the heat exchange, to estimate how many grams of magma I need each second to convert my crude oil into petroleum. And over here on the right, we have the number of seconds that have elapsed since the experiment began. It runs faster than seconds because I've got this fast speed mode. And over here is the number of beads of magma that have been used in this specific tile here. But the beads here are 3 kilograms, so if you want to know how many kilograms of magma, you have to multiply by 3. And if you do this times 3 divided by that, it gives you a number of kilograms per second. And if you set the thermosensor here at 401, then you consume 534 grams per second of magma. On the other hand, if you set this thermosensor to 403, then you consume about 550 grams per second of magma. All volcanoes have at least 800 grams per second on average. But what if you have something smaller like a minor volcano? Well, a minor volcano on average will provide 550 grams per second. So in that situation, if you're a little bit not sure you're going to have enough magma, maybe 401 will be better. But to tell you the truth, what you should do if you really don't have enough magma is you should use a model that has more of these. So the heat exchange here is not very long. You can make the heat exchange longer, and you can also try to drain more of the heat from your magma. So I had a previous model in a previous video, which is somewhere here, which looks much more intimidating, but this one uses about 200 grams per second. So you could run 2 of these even on the smallest minor volcano that's in the game. The reason why I show this system is because I think this is a much more realistic. I mean, the other one had, I don't even know how many of these layers it had. Just so we see, the length of this here is 14 tiles. So if you 14 tiles and then you just do 1, 2, 3, and that's it. This is your heat exchanger. This is your petroleum boiler. Now I promised that I would show you the let me show you here. I promised that I would show you the magma pump, but of course I advise you that you should go look at my other video, which has a lot more information about this. Now, this is a fix magma pump. That's the name of the poster on the Clay forums who originally posted this type of magma pump. And the way, so first of all, I've got the crude oil coming here. I don't need the crude oil for this. I'm just using it as coolant for my pump. So the crude oil is at 80 degrees, and that's just fine. I've got a magma pump here. Actually, I've made it out of steel. You don't need it to be out of steel. You could make it out of gold amalgam, maybe. And the deal is that if you can see the cross shape in the user interface, this magma pump is able to draw a liquid from any one of these 5 tiles, and you can see that therefore it can draw liquid from the magma. But the condition is that the magma pump should be immersed, and you can see from this little red icon right now that the magma pump is not immersed. In order for it to be immersed, the 4 tiles which are here, one of these tiles should have a fluid behind it, and so the secret is to just put a drop of a liquid, which I'm using Naphtha because this is the liquid that Fix used. But you have to be careful that the liquid that's on here doesn't drip into the magma, because then you'll be in trouble, because you need this, everything here is in a vacuum. Now you'll see that the liquid vent here is closed, so this prevents the naphtha from flowing here, and therefore this pump is not immersed, which is what it's saying, and therefore there's no magma being pumped. And that's the automation from the liquid reservoir here, because the liquid reservoir is sufficiently full right now that it doesn't want to have any more magma. But when the liquid reservoir wants more magma, it'll use the automation to open this liquid vent, which is going to allow a drop of naphtha to drop here. Now I can force it with this signal switch here, which you don't need to put in your build. This is for me to force this vent open, so I'm going to do that now. And so now this vent is ejecting little beads of naphtha which are dropping here. And this is just enough. If we look at the materials, we see the naphtha blinking in and out of existence on this tile here, and it never drips into the magma. And so then this magma pump, this pump draws, it alternates between drawing the little bead of naphtha and then drawing a little bit of magma. And we can see that we have a little, this is a sort of a homemade filter, if you want. You might be more familiar with the liquid filter that looks like this, that you can use to separate. You can use this to separate the naphtha and the magma, which you need to do. But this filter here will heat up because it has plus 4 kDTUs of heat per second. So it's a little bit hard to keep cool because inside of this thing will be magma. So you want to be careful that the magma inside of that thing isn't gonna interact with, if you have to put it in an atmosphere to keep it cool, or if you have to put a bead of liquid on top of it, you have to make sure that it's not going to interact with the magma, which is very difficult. So that's why I use a liquid pipe element sensor followed by a liquid shutoff, and this allows me to select the naphtha and send it to up this way, and the magma send it the other way. And I have a liquid valve here so that I don't have too much naphtha on top of this tile here, and it doesn't drop into the magma. The liquid valve is set to 1 kilogram per second, 1,000 grams per second, because you can get maybe, I don't know how many kilograms you can have on top of this thing here, but 1 or 2 is okay. It's not gonna drop into the magma. If it drops into the magma, you're gonna create sour gas, and as soon as there's a little bit of sour gas, all this stuff here is going to overheat and melt and break, and you're going to be in trouble. The naphtha sort of flows in a loop here, but there's a pass through here, because if I close the vent, in principle you can see the little beads of naphtha moving towards the vent. If there was no pass-through over the vent, all these beads of naphtha would accumulate, so that when the vent would open again, there would be 10 kilograms of naphtha that would drop, and then that 10 kilogram would spill into the magma, and then would be trouble. So there's a little bypass here where the naphtha is able to get around. If the vent is closed as it is now, it just keeps going in circles. So this is my simple mid-game petroleum boiler that uses piped magma